Alright, in this video we're going over rational functions and their graphs. Alright, here's your vocabulary. First word, rational function is simply a function that you can write in the form of f of x equals p of x over q of x. So you have some function, some polynomial over another polynomial. A continuous graph is a graph with no jumps, breaks, or holes. Meaning, if you put your pencil down on the left side of your paper, you could draw the entire graph without picking up your pencil. Discontinuous graph, a graph with jumps, breaks, and or holes. Meaning, if you put your pencil down on your paper to draw your graph, you'd have to pick it up at least once to draw your graph. All right. Now, these three highlighted words are also vocab. They're called points of discontinuity. So, if a is a real number for which the denominator of a rational function, f of x, is 0, then a is not in the domain of f of x, the graph of f of x is not continuous at x equals a, and the function has a point of discontinuity at a. Points of discontinuity basically is when you have a point where your graph is not defined. Okay? There's two types of discontinuity. There's removable. The reason this one's called removable is because these two factors here will cancel out, leaving you just x plus 3. All right? So your graph is still undefined at x equals -2 along your actual graph. So this will look like the graph of x plus 3. So if you graphed it, you'd have 1, 2, 3. So it would go up like this. Well, at -2, you'd have a hole. At x equals -2, there'd be a hole in the graph. All right? But the reason it's called a removable discontinuity is because you can cross this out, and then you just have y equals x plus 3. And if you plug in -2, you're going to get -2 plus 3, which is +1. So at -2, this graph will equal +1. All right, so that's what's called a removable discontinuity, is when you can cancel out your entire denominator. Well, let me rephrase that. Not the entire denominator. When you can cancel out parts of the denominator with the numerator, that becomes a removable discontinuity. Now, a non-removable discontinuity is when there's no way to cancel out part or all of the denominator. Like in this case, you have x plus 4 over x minus 2. You have a non-removable discontinuity at x equals 2 because there's no way to get that x minus 2 out of the denominator. So that's a non-removable discontinuity, where here we can get the x plus 2 out of the denominator. So therefore it is a removable discontinuity. All right, you just plug in, and then you're just left with y equals x plus 3. You plug in the point where you have your discontinuity, and then you solve, and then you've basically now redefined the function at -2. Okay? We're going to do some examples, so if that's confusing. All right, number 1, finding points of discontinuity. Well, points of discontinuity only occur at where your denominator is going to equal 0. All right, it's only going to occur where your denominator equals 0. So let's look at this first one here. We have y equals x minus 5 over x squared plus 1. All right, is this denominator ever going to equal 0? Let's find out. So x squared plus 1 equals 0. Minus 1, x squared equals -1. Are there any real numbers that we can multiply together, or that we can square? Any real numbers that we can square and get a -1? No. So which means this has no discontinuities. Okay? I'm going to put no DIS. No discontinuities. Because you can't get this denominator equal to 0. So since you cannot get the denominator equal to 0, you don't have any discontinuities. All right, let's look at this guy. Well, down here we have a polynomial. So the first thing that we're going to need to do when we see this is factor any polynomials. All right? So x squared can only factor into x and x. Plus here means both our signs are the same. This means they're both negative. The only factors of 3 are 3 and 1. Okay, the only factors of 3 are 3 and 1. So, here we go. Well, x minus 3 equals, whoops. So let's set both of these equal to 0. So we have x minus 3 equals 0, plus 3, plus 3, x equals 3. So x minus 1 equals 0, plus 1, plus 1. So x equals 1. So this graph is said to have two discontinuities at 1 and 3. All right. Now, let's see if we can remove any of these. Remember, in order to remove it, we need to be able to cancel out all or part of the denominator. Well, in our numerator here, we have an x plus 3. But in our denominator, we do not have any x plus 3s. So therefore, x equals 3 and x equals 1 are called non-removable discontinuities. Because, that's an S, because we can't get rid of either one of these. If this had been an x minus 3, or this had been an x plus 3, we could have canceled here, so then this would have been a removable discontinuity, and then 1 would have been a non-removable. The next example is going to show us about the non-removables. Okay? But for this one, since we can't cancel out any of these two factors with the top, both of these are considered non-removable discontinuities. All right, now let's look at this one. Again, here we have a polynomial, so let's factor. So x can only factor into x and x. We have a negative, so we know both our signs are, we have one of each basically. This negative tells us our larger factor is negative. So what multiplies to 4 and adds to 3? Well, that's going to have to be 4 and 1. All right, over x minus 4. So now we take the denominator, set it equal to 0. So we take x minus 4, set it equal to 0, add the 4, and the 4. So x equals 4. All right, so we know we have a discontinuity of some kind at x equals 4. But now if you look, we can cancel this x minus 4 with this x minus 4, leaving us just x plus 1. Okay? Since we can cancel it out, that tells us that we have a removable discontinuity at x equals 4, because we can physically get that out of the equation. Since we can physically get it out of the equation, we have what's called a removable discontinuity. Okay, so we have a removable discontinuity at x equals 4. All right. Now, in order to define this graph at x equals 4, what we can do now is take our x equals 4, plug it in to our new function. I'm going to call it new function. It's really the same one, but we plug it in here to our simplified function. Okay, so we have y equals x plus 1. Substitute in the 4. So we have y equals 5. All right. So what we can actually do now is we can redefine this function so that it has a value at x equals 4, because normally this function does not have a value at x equals 4. So what we can do is this. We can go y equals, all right, draw your little curly bracket. Now, write in your original function on top, so x squared minus 3x minus 4 over x minus 4, all right, comma, if x does not equal 4. All right, so as we've determined here, this function right here, we cannot plug in x equals 4. All right, so we're saying that y equals this function if x does not equal 4. Okay, but now, what if x equals 4? Okay, so now we're defining it at x equals 4. Well, right up here, when we plugged in the 4, we got y equals 5. Okay, so we know that y equals 5 if x equals 4. Okay, so now we have taken and we have redefined this function so we can get a value at 5. I mean at 4. Okay, so this function is now defined everywhere. Okay, for all real numbers. So if x is not 4, y equals this function. If x equals 4, then y just simply equals 5. Okay? Oops, too far. Vertical asymptotes. What are the vertical asymptotes for this graph? Vertical asymptotes are the easiest thing in the world to find, okay? Because vertical asymptotes, VA, only occur when your denominator, I'm just going to put denominator equals 0, okay? So here we have x plus 1 over x minus 2 times x minus 3. So our vertical asymptotes only occur when the bottom of your function equals 0, okay? Only when the bottom equals 0. So what we're going to do is we're going to take x minus 2, set it equal to 0, solve for x, so add 2, and 2, so x equals 2. We're going to do the same thing with the 3, and the 3, and the 3, so x equals 3. Okay, so we have two vertical asymptotes at x equals 2 and x equals 3. Now, how do we know? All right, now let's go into horizontal asymptotes. This is what you're going to need to remember here. Okay, m and n are the degree of the numerator and the degree of the denominator. Okay, so if the degree of the numerator is smaller, if the degree of the numerator is smaller than the degree of the denominator, okay? Remember, the degree is your highest exponent. So if your numerator has a smaller degree than your denominator, your vertical asymptote is simply y equals 0, which is the x-axis. Okay, I'd write this down. If the degree of the numerator is larger than the denominator, you're going to have no horizontal asymptote. All right? Now, if they're equal, it's simply going to be y equals the leading coefficient of the top divided by the leading coefficient of the bottom. All right, I know that sounds confusing. Let's look at a few of these. Make sure you write this down. Okay, make sure you write this down. So let's look at these three examples here. First, we want to identify the degree of the top and the degree of the bottom. So the degree of the top is 1 because that's our largest exponent. The degree of the bottom is also 1, so that's our largest exponent. So if you look back at that chart, when the degrees are equal, like in this case, they're both 1, when the degrees are equal, it's simply the leading coefficient of the top here, which is 2, because remember, your leading coefficient is the coefficient on the variable with the highest exponent. So that's going to be 2. Leading coefficient here is 1, so it's going to be y equals 2 over 1, or just simply the line y equals 2. That is going to be your horizontal asymptote. All right? Let's look at this one. Here, the top is 1, the bottom is 2. So the top is less than the bottom. Okay, so 1 is less than 2, so the top is less than the bottom. So it's simply going to be the line y equals 0. Okay, it's simply going to be the line y equals 0. All right. Now if we look at this one, the degree of the top is 2, the degree of the bottom is 1. So if you look back at that chart, since the degree of the top is greater than the degree of the bottom, this function will have no horizontal asymptote. Okay, that will have no horizontal asymptotes. Okay, and remember, asymptotes on a graph is where the function is not defined. Okay, your graph will never cross an asymptote because the graph is not defined at asymptotes. Okay, because think about it, with vertical asymptotes, they occur where your denominator equals 0. Can't divide by 0, so therefore you have a vertical asymptote because anywhere along that line, your graph is going to be undefined. Same thing with horizontal asymptotes. It's where your graph is undefined. So your graph will never cross nor touch an asymptote. It can get really, really, really close, but it will never cross nor touch an asymptote. All right? So that's the end of this lesson. Make sure you take notes. Feel free to watch it as many times as you need to. Make sure when you come to class tomorrow, you're ready to work some problems. See you tomorrow.